let us look at the problem of a harmonic oscillator. So, what is a harmonic oscillator? I have discussed it several times, but today now we are going to discuss it in great amount of detail. The simplest example that I can think of is a hydrogen atom attached to the surface of tungsten by a chemical bond, of course. And if you, as I had been repeatedly saying, if you displace it in one direction, in that direction and release it, it will execute vibrational motion. Why does it execute vibrational motion? Because when I have displaced it to this position, the bond between the hydrogen and the tungsten has been stretched, right, and so there will be a restoring force trying to bring the atom back to the equilibrium position. And the simplest thing is to say that that restoring force is proportional to the amount by which I have displaced the atom. So, if x is the displacement of the atom from the equilibrium position, the restoring force trying to bring it back to the original equilibrium position will be equal to k times x with a negative sign. The negative sign is put because it is in the opposite direction. So, this will be the restoring force, and you know that in such a problem what will happen, this is the restoring force. So, therefore, if I am using Newton's equations of motion, what I will have to say is mass into acceleration would be equal to, see the particle is subjected to this restoring force. So, therefore, what will happen, it will move, it will get accelerated because a force is acting on the particle, and the Newton's equations will simply tell me that mass into acceleration must be equal to that force minus kx. But acceleration is what? Acceleration is rate of change of velocity, right. So, it is rate of change of velocity. So, I naturally have to have dv by dt, but v itself is nothing but rate of change of position. So, therefore, acceleration is nothing but the second derivative of the position of the particle, and hence what happens to this equation? This equation becomes m into d square x by dt square is equal to minus kx. A simple differential equation, very easy to solve. I shall just say that the solution of this equation may be written as x of t equal to some x0 cosine of 2 pi nu t. This is the solution, where I have assumed that the particle has been initially displaced to a position which I denote as x0. What I am saying is I have my particle at the equilibrium position. Initially what I have done is I have moved it and put it into a new position such that the displacement is x0, then this is the solution, right. And this nu, you can actually substitute this into that differential equation and get an expression for nu. What you will find is that this nu must be equal to 1 by 2 pi into square root of k by m. Very easy to do, that is why I am not doing it. You can take this solution, substitute into the differential equation, and you will see that the differential equation is satisfied by that solution, provided I take nu to be equal to 1 by 2 pi into square root of k by m. And what it means is basically simple, because it must be very familiar to all of you. I am not describing this in detail, but what it means is that the particle will actually execute oscillations. A classical mechanical particle will execute oscillations. It will oscillate that many number of times per unit time, and hence this is known as the frequency of vibration of the oscillator. Okay. And further, if I was using classical mechanics, you see I can actually displace it by any amount. The spring is assumed to be completely elastic. Even if I stretched it by a large amount, it will not break. That is the assumption in this model. So, therefore, I can displace it by any arbitrary amount, and depending upon how much I have displaced, the energy of the system will be different. If I displace it by a small amount, energy will be small. If I displace it by a large amount, energy will be large. And therefore, classical mechanically speaking, the system can have any energy starting from 0 to infinity, continuously energy can be varied if you want, you can give it any energy. So, there is no quantization at the classical level, all energies are permissible. And one more thing that I want to say is, you see, if you have such a restoring force, what is the potential energy that is characteristic of the system? The answer is that the potential energy must be defined by V of x equal to half k x square. This essentially means that the amount of work that you have to do in order to displace the particle from the equilibrium position to a new position goes quadratically with that position, right. If you wanted to displace the particle by an x, the amount of energy or amount of work that you have to do, amount of energy that you have to supply, or the amount of work that you have to do will go like x square. That is the meaning of saying that the potential energy of the system is quadratic in x. So, therefore, you have V of x equal to half k x square. This also can be derived, but I am not going to do it. Starting from this force, it is easy to show that this must be the expression for the potential energy. So, what is of interest to us is not the classical mechanics of the system, but the quantum mechanics of the system. So, we will worry about the Schrodinger equation for the system. What is the Schrodinger equation? The Schrodinger equation is minus h cross square by 2m dou square upon dou x square plus half k x square. Remember, that is the potential energy of the system operating upon psi of x must be equal to E times psi of x. Now, this potential energy I would like to represent it in a figure. So, how will it look like? Along the horizontal axis is the displacement from equilibrium position. The displacement can be in the positive direction or it can be in the negative direction, right. So, what will happen? The potential energy is just assumed to be half k x square. So, it is natural that the plot of potential energy against x will resemble a parabola looking like that. Okay. That is probably the best parabola that I can draw. So, it has this appearance. This is V of x plotted as a function of x. Actually, strictly if you think about this model is not a very good description. The reason is that, see, even if you supply a large amount of energy, what will happen is that the distance will only increase, right. The distance will increase, I mean the amplitude of vibrations will increase and it will vibrate with a larger and larger amplitude. But if I had an actual hydrogen atom attached to tungsten and if I went on supplying energy to the bond, what will happen is that the bond will eventually break, and once the bond is broken, the atom will go away. So, the process of dissociation will take place, but this model has the defect that the atom will never detach from the surface, it will just go on vibrating. Okay. So, therefore, this is defective, but then if you are interested in vibrations which are not very large amplitudes, then this is not a bad model. Okay. So, we think of this a very idealized model, and the model is very useful because the quantum mechanics for it can be exactly solved. Okay. So, what we want to do is we want to solve this equation, and the potential energy behaves like this, and of course, you see your wave function, you will want it to be continuous, you will want it to be single valued, and also you will want it to be normalizable, right. All these things have to be satisfied. In particular, I can say the following thing physically. Suppose the wave function looks maybe something like that. Okay. Now, I can definitely say that, see, if we are going in the for large values of x, there the probability of finding the particle has to be decreasing. Why? Because when the value of x is very large, the potential energy is getting very large. So, in this region the potential energy is extremely large and my particle has only a finite amount of energy, and therefore, I would not expect this particle to penetrate far into this region. We have seen in the morning that if you had a potential which was like that, the particle actually does penetrate a little bit into the barrier region, but that was rather small. Similarly, here also I would expect that the wave function will penetrate into this region, but I would expect that at infinitely far away from the equilibrium position, I would expect that the probability will definitely vanish, and therefore, I will have to solve this equation subject to the condition that psi of x, I will impose the condition that it has to approach 0 when x approaches infinity, not only plus infinity, but also when x approaches minus infinity. So, this is something that I will have to impose. If I find a solution which does not obey this, then I am not going to accept that, that is not physically sensible. Any physically sensible solution has to satisfy the condition that when x approaches plus infinity or minus infinity, the solution should approach 0. Okay. So, now I am going to worry about this equation. I want to solve this equation, but the way this equation is written, you have minus h cross square, then there is a 2m, there is a k, there is also energy, and you would agree with me when I say that there are many constants. Okay. There are many constants m, h cross, k and e, and I want to have only the minimum number of constants. So, what am I going to do? Well, I am going to introduce one more constant. I want to get rid of all these constants, but that I do by introducing one more constant. So, what I will do is I will define a new variable which I will denote as c, this symbol is c xi, and I will say that it is equal to a constant alpha times x. Okay. Alpha is a constant, I am going to determine it, right, and I will determine it in such a fashion that the equation has the nicest possible appearance. That is the way in which I will do it. So, if you introduce such a variable, what will happen? You can say this means that x is equal to c divided by alpha, and further you can also say that dx, alpha is a constant, so dx must be equal to dc divided by alpha. Agreed? And therefore, d by dx would be equal to how much? Well, you can use this, you will say okay, it is actually alpha d by dc, correct. So, I am going to use that in here, and if I use that in here, what will happen? My h minus h cross square upon 2m, I have second derivative with respect to x. Here this is actually the first derivative, but it is very easy to calculate the second derivative from here, right. Because alpha is just a constant. So, therefore, what will happen is that d square upon dx square will be nothing but alpha square d square upon dc square. Notice also that you see here I was using partial derivative notation, which really is not needed. So, I am not writing it anymore. Why? Because this operator is going to operate only upon psi, which is a function of x alone, only one variable is there in psi. So, this is that equation, and what will happen, I have plus 1 by 2 k. I decided that I do not want x, but I want c. So, therefore, that is going to be c square by alpha square, and the whole thing is going to operate upon psi. Psi will now be considered as a function of the new variable c, right. It is going to be considered as a function of new variable. It was a function of x, but now it is a function of c, and this is equal to E psi, that is the equation. Now, still you see I have seem to have introduced an additional constant which I do not even know, but what I will do is I will divide throughout by this factor. So, if I divide it throughout by that factor, what will happen, I will get minus d square upon dx c square plus 1 by 2 k divided by alpha square into 2m divided by h cross square alpha square into c square. And on the right hand side you are going to have 2m e divided by h cross square alpha square into psi. Now, you see at this point I do not seem to have attained anything by introducing this additional constant alpha, but what I will do is I will say I am going to choose alpha in such a fashion that this is equal to 1. That I can always do, right. Alpha is undefined, but now I say okay, let me choose alpha in such a fashion that that is equal to 1. If you look at that expression, actually there is a half here, but this half and that too can be removed. So, essentially I can attain that by defining what should be my definition of alpha. If I define alpha to be k into m divided by h cross square to the power of how much? See, I want this to be equal to 1. So, what should I choose alpha to be? It has to be k into m by h cross square to the power of 1 by 4, right. If I chose that, then I am happy because this is equal to 1, and at least my left hand side looks very nice, because it is minus d square upon dx c square plus c square. What about my right hand side? I am going to evaluate this object 2m e by h cross square alpha square. Where will I evaluate it? Maybe here 2m e divided by h cross square alpha square, but alpha is so much. So, this is going to be actually k m divided by h cross square to the power of half. This is that object. Now, you can simplify this. Well, you can very easily work it out. What is going to happen is you will have that okay? Cancelling out, say this if you took the square root, this h cross square will become h cross, and that will cancel one of the h crosses, because there are 2 h crosses here. So, that is why you get h cross. Then there is an m here, there is a square root of m here. So, naturally you will get square root of m in the numerator. And if you like, you can write this as 2e divided by h cross square root of k by m, and that you can write as 2E divided by h divided by 2 pi into square root of h cross, after all is just h divided by 2 pi. Right, and that again is nice because you have 1 by 2 pi into square root of k by m. That is nothing but your classical frequency of vibration of the harmonic oscillator, and hence you can say this is nothing but 2E. E is, remember, the energy of the particle, and this object that you have there is 2E by h nu. So, this constant that is occurring on the right hand side is just 2E by h nu. Right, but then again the writing 2E by h nu is tedious again, and I have to write it again and again and again. So, what I will do is I will call this lambda. That saves me the trouble of writing this again and again, and therefore, what has happened to my differential equation? My differential equation now looks much better than earlier. The way it looks is minus d square upon dx square plus c square operating upon psi is equal to 2E by h cross square alpha square, but that is actually something that we have calculated, it is equal to lambda, that is the notation. So, lambda times psi. And now things are nice because I have only one constant in my equation, and that constant is lambda, and that constant is related to the energy of the particle, correct. It is now, it is actually E divided by h nu, 2E by h nu. So, I would now like to try and solve this equation. So, let me rearrange this equation. How can I write this? It may be written as d square psi by dx square plus lambda minus c square. Think about it for a second, you would realize that this is the way you can rearrange this equation. So, the only thing that is, I mean, a constant here, right, the only unknown, no, I should not say unknown, the only parameter that I have here is now lambda. Okay. So, we want to solve this equation, and now how do we solve this equation? Well, the way in which I am going to solve this equation is interesting. The first thing that I will do is I will claim that psi equal to any constant times e to the power of minus c square by 2 will be what I refer to as an asymptotic solution of the differential equation. So, what do I mean by asymptotic solution? The answer is that this is a solution that is valid for large values of c. Suppose c is very large, that means you are far away from c equal to 0. Suppose you are far away from c equal to 0, in fact c is much larger than 1 and so on. So, if you are very far away from the origin, c will be very large, and if you are in such a region, you have c square here, what you can do is you do not have to worry about this lambda in comparison with that c square, because c square is very large. So, in that region, in the asymptotic region, this differential equation will become d square psi by dx square minus c square psi is equal to 0. This is the form of the differential equation in the asymptotic region where c is very large. But now you look at this function. Let me denote this function temporarily by the symbol f, which is a function of c. It is equal to a e to the power of minus c square by 2, right. The function is defined to be this. Suppose you take its first derivative, df by dx will be how much? Well, it is fairly simple and straightforward. It is going to be equal to minus c times a e to the power of minus c square by 2, correct. If you took this function, took its first derivative, that is the answer. If you took its second derivative, what will be the answer that you are going to get? Well, second derivative means you actually have to differentiate this term. So, you will get minus a e to the power of minus c square by 2 plus c square a e to the power of minus c square by 2. This is what you will get. The second derivative is equal to that, which actually says that the second derivative is equal to minus of the function f of c plus c square into the function f of c. So, this is the differential equation that f of c obeys. But then if you are in the large c region, right, you have c square here, you have instead of c square you have 1 there. Here if you want, you can say there is a 1 there and there is a c square here. So, if c is very large, this 1 and that c square you can compare, and you can definitely neglect this 1 in comparison with c square. So, essentially what I am saying is, you look at this may be written as c square minus 1 into f of c. This equation as it is may be written as c square minus 1 into c, and if c is very large, definitely this 1 can be neglected in comparison with c square, and so let me neglect that, and then what happens, this differential equation d square f by dc square is equal to c square times f of c, which is exactly the same differential equation as the one obeyed by psi. And therefore, what is the conclusion? In the large c region, psi, a possible solution of this equation is psi is equal to that function f. And so, what I have proved is that psi equal to a e to the power of minus c square by 2 is an asymptotic solution. It is valid only in the large c region, it is not valid near the origin, it is not valid near c equal to 0, but it is valid when c is very, very large. This is a solution. But then you may say, well, you can also think of another solution which is of the form b e to the power of plus c square. The same procedure you can try, the same procedure, differentiate it 2 times, you will find that this also satisfies the same differential equation. Not surprising, because this is a second order differential equation, there should be 2 solutions, 2 independent solutions. So, the most general solution in the asymptotic region will be a combination of these two, a into e to the power of minus c square by 2 plus b into e to the power of plus c square by 2. But then, having seen that, what will you say? Is this an acceptable solution? Well, you have problems with this if you say this is the solution. The problem is that as the value of c becomes very large, this term becomes extremely large, it actually goes to infinity in the limit c goes to infinity, and therefore, you will have to say that b has to be 0, there is no other way. So, therefore, the only possibility is that you have this as the asymptotic solution, not the other one. In order that the solution is acceptable, asymptotically the solution must resemble some constant into e to the power of minus c square. But this is valid, the solution is correct only for large values of c, it is not valid for small values of c. So, what I am going to do is, I am going to take this solution. What is the solution? The solution is actually psi equal to some constant into e to the power of minus c square by 2, that is what it is, right, there is a constant there. But I want to make this function a solution even for small values of c. Definitely it is not a solution, but maybe what I can do is I can replace this constant by a function of c. What will this function do? It will adjust things in such a fashion that this product will become a solution everywhere, not only when C is infinity, C is very large, not infinity, but very large, even when C is very small, this H will see to it that that is a solution, right. So, if that is the way it is, what can I do? I will now have to find H. So, how will I find H is the next question. Well, the way to find the function H is, I will take this, I will assume that this is a solution and take that solution and put it into the original differential equation that I want to be satisfied. I want this equation to be satisfied. So, let me take this H, this psi and put it into that differential equation which psi has to obey. Right. So, we will have to find H, that is what we will do. For that we will take this and put it in here and find the equation for H, but of course, any H that I find has to be satisfying this condition. What is the condition? As the value of x becomes very large, which actually means when the value of C becomes very large, any H that you find has to satisfy the condition that H into e to the power of minus c square by 2 has to approach 0, that has to be satisfied. Any solution that I find for H, any thing that I have for H has to satisfy the condition that this will approach 0 as C approaches infinity, otherwise I am not going to have an acceptable wave function. So, let me now take this and put it in here and see what happens to this differential equation. So, to do that, let me first evaluate d psi by dc. It is going to be dH by dc. Okay, H actually depends upon C, but let me save some trouble by not writing that C within the brackets, into e to the power of minus c square by 2 plus H into minus c e to the power of minus c square by 2. Okay, this can be confusing because you may think that this is a function of c. So, what I will do is I will put minus c on this side, that is what it is. So, that is the first derivative. How about the second derivative? Well, let me just go ahead and differentiate. I will get d square h by dc square e to the power of minus c square by 2. Then if you just carry out the differentiation, you have to differentiate this, that will give me a minus c dh by dc e to the power of minus c square by 2. Then from here I will get a minus h e to the power of minus c square by 2, that is only one term, but I have additional terms. I will also have minus c dh by dc e to the power of minus c square by 2. I am not done because there is one more term, and what is that term? That is going to be plus c square h e to the power of minus c square by 2. So, this is the full set of terms that result when you carry out this differentiation. In fact, if you look at this expression, you will notice that the second and the fourth terms, they are the same. So, they may be added up, this term and that term, you will find they are the same. So, you can say this is actually d square h by dc square e to the power of minus c square by 2 minus 2c dh by dc e to the power of minus c square by 2. These two terms I have added up, plus what will happen, I will get c square minus 1, this term and that term I am combining, h e to the power of minus c square by 2. This is what happens. So, the next thing that I should do is I should take this expression, put it here and add lambda minus e square into psi to it. So, instead of taking it there, what I will do is to this right hand side that I have here, which is sitting here, I am going to add the term. Well, let me remove this equal sign, because this is the second derivative. I have determined it. This is the second derivative of psi. To that, all that I need to do is I have to add lambda minus c square into psi here, but psi is e to the power of minus c square by 2 into h, and this should be equal to 0. That is the differential equation. But once you look at that equation, you would see that it can be simplified, because e to the power of minus c square is sitting everywhere. Just divide throughout by that. That makes it look nicer. This goes, this also goes. But that is not all. There is a plus c square minus, sorry, plus c square here, and there is a minus c square there. So, this term and that term will cancel, and I will be left with d square h by dc square minus 2c dh by dc plus what happens, what do I have left? This and that will cancel. So, I would have lambda minus 1 h is equal to 0. Well, when you look at it, you really wonder, because this was your original equation, and I have arrived at another equation, and it does not appear much simpler, right? This equation and that equation, if you compare, they do not appear, I mean, one does not appear to be much simpler than the other, but the interesting thing is that it is actually easy to solve this equation. It is quite easy to solve this equation. We will discuss that in the next lecture, but it has to be solved subject to the condition that psi equal to e to the power of minus c square by 2 into h should approach 0 as c approaches either plus infinity or minus infinity. It has to be solved subject to that condition, and that is what we will do in the next lecture. Thank you for listening.